Okay, we're still in 2.6 of Barnett, logarithmic functions. And next we'll look at applying log functions and properties of log functions, as well as evaluating some of these log functions. Okay, so let's see. The log function with base 2 is defined to be the inverse of the one-to-one exponential function y equals 2 to the x, which we looked at in the previous section. So here we have the graph of y equals 2 to the x. Notice it approaches the negative x-axis as x gets large, and it passes through 0, 1. Okay, so as x gets large, in the negative way, you should say here, right? Because that's when we're approaching the negative x-axis. Okay, as x gets large, negatively. Okay, so notice that this exponential function, y equals 2 to the x, well, it's 1 to 1. Why is it 1 to 1? Because it passes the horizontal line test, right? I could draw many horizontal lines here, hopefully better looking than this last one, and they will only cross the graph of my function once, at only one point. So since it passes the horizontal line test, it is 1 to 1, and if it is 1 to 1, it must have an inverse. Okay, that's what we discussed in the last video. So let's start with y equals 2 to the x. Let's find this inverse. And we do what we did before in Algebra 2, which is what you've probably seen in high school or in your last math class. You interchange x and y coordinates, right? Remember, we said that if a comma b is a point on the graph of f, then b comma a is a point on the graph of f inverse, right? You just interchange the x and y coordinates. So switching the x and the y gives me x equals 2 to the y. Okay, so I get x equals 2 to the y, but there are no algebraic techniques that can be used to solve for y. So we simply call this function y the logarithmic function with base 2. The definition here that we have, the formal definition of this new function is as such. Log base 2 of x is equal to y if and only if x is equal to 2 to the power of y. So you see the log base 2 of x, that really means a power, right? Since it equals to y, and y is just a power. The log is just a power. Log is just an exponent. Okay? Every time you see log thing, find the exponent. Here's what we mean. The inverse of an exponential function is called a logarithmic, or log for short, function. For b bigger than 0 and b different than 1, y equal log base b of x is equivalent to saying x equals to b to the power of y. This is wrong here. Sorry about that. This should say b to the power of y. Okay? So, b to what power? B to the power of y should give me x. That's what we're looking for, the power of y, when we see log base b of x. Right? We're looking for what power do we need to raise b, the base, in order to get x. Okay? So the log to the base b of x is the exponent to which b must be raised to obtain x. Okay, so the domain of the log function is the set of all positive real numbers, and the range of the log function is the set of all real numbers. Okay, just as we would expect based on our conversation for exponentials. Now take a look at this. In this slide we have the graph of y equals 2 to the x, the exponential function here, and then we have its inverse, the log function, y equals log base 2 of x, or equivalently x equals 2 to the power of y. We've obtained these using tables, which you could see here, by just reversing the ordered pairs, right, to get the to get the inverse function. And what I want you to notice, if you draw the line y equals to x, one graph is really the mirror image of the other over that line, y equals to x. So you could see that the logarithmic function y equals log base 2 of x is the reflection of the exponential function y equals 2 to the x over the line y equals to x. This happens to be a general property for inverse functions. If you were to graph two functions that are inverses to each other on the same grid, the graph of one is always going to be a reflection of the graph of the other over this line, y equals to x. Okay, so let's take a look at the next slide here. Talks about the graph domain and range of log functions. The domain of the log function y equals log base 2 of x, it says is the same as the range of the exponential function y equals 2 to the x. Why? Well, remember, to obtain the log function, you change the coordinates of this function, the exponential function 2 to the x, by reversing them, right? By flipping the x with the y. So you obtain b comma a as the coordinates of f inverse, which was the log base 2 function, right? This was your main function, 2 to the x. So that is why it makes sense to say that the domain of one became the range of the other, and vice versa. The range of the original became the domain of the inverse. And that's exactly what we have here. The range of the log function is the same as the domain of the exponential function for the same reason. Another fact, as I already stated, if one graphs any one-to-one function and its inverse on the same grid, the two graphs will always be symmetric with respect to the line y equals to x. Keep that in mind. Okay, why don't we get some practice in evaluating these logs? Okay, so study these examples and you should be able to convert a log into an exponential and vice versa. So I'm going to do the first example to decide, even though you have it done. It says log base 4 of 16 is equal to x. So right away, again, every time you see log of something, base anything, that just means find me the exponent, right? So x here is some exponent. In fact, converting this to exponential form, you're really asking the base 4 raised to what power x will give me 16. Well, and the answer is 2, because 4 squared is 16. Okay? Look at number 2. If I told you log base 3 of 1/27, and I asked you to find that, what am I really asking you to find? I'm asking you to find 3 to what power will give me 1/27. Let's call the power x again. Okay? So 3 to what power will give me 1/27? Well, remember that 1/27 is really the same as 3 cubed, and 1/3 cubed is the same as 3 to the negative third power. So we have 3 to the power of x equals 3 to the negative third power. X better be negative 3. Okay? That's how we find the power there. Look at number 3. We're going in the other direction now. We start with 125 equals 5 cubed. That's an exponential expression. And what we're saying is we can convert this into a log expression. We can instead say log base 5 of 125 is equal to 3. Because log base 5 of 125 means to what power do I raise 5 in order to get 125? And the answer would be 3. Likewise, for the last equation here, number 4, we have square root of 81 is equal to 9. Okay, this could be rewritten as 81 to the 1/2 power. That's what they have right above. 1/2 represents square root, remember, equals 9. Or you could say log base of 81 of 9 equals 1/2. Because this last log expression means 81 to what power will give me 9.